Okay, friends, let's get started. As you've no doubt noticed, we're a lecture or two behind. That happens always in this part of the semester. I'm always overly optimistic with what's on the syllabus. Just understand that we probably aren't going to get to chapter 4 prior to the exam, and therefore I would not, if we don't, which is 100% likely, I won't put chapter 4 on the exam, right? Okay. And I will try to update the syllabus with sort of a new estimated schedule, but again, the study guides aren't going to be due till after the exam anyway, so hopefully that helps, and I'll send out more information in terms of schedule later. Now, we have been talking about acids, bases, and pKa's. Recall that pKa is a number that tells us how acidic an acid is. Remember that lower or more negative pKa's are stronger acids. Recall that more acidic groups are going to have lower energy sigma stars that a base can attack to remove the proton. And then this is very important. Recall that strong acids are strong because their conjugate bases can tolerate a negative charge or extra electron density. And we're going to use that to rationalize why the differences in acidity between different acid groups. These pKa's aren't really to memorize. You'll have a pKa table with the data that you need, except of course for the most important ones, which are -2 for hydronium or oxonium, losing a proton to become water or an alcohol respectively. And then the other one to memorize is one we'll get to in a second. That is the pKa of water or an alcohol going to losing a proton to become hydroxide or alkoxide respectively, and that's 16. And remember that with each pKa unit, each 1 unit difference in pKa, we're talking about a factor of 10 in acidity. So we would say, for example, that hydronium is 10 to the 13 times less acidic than HI. All right. So I think when we left off, we had gotten sort of to HF, and we're going to talk about trends that explain some of these differences in acidity among the halides and then elsewhere. Also about a pKa of 4 is this carboxylic acid. You'll get good at recognizing that functional group. Sometimes it's abbreviated RCO2H by folks who don't want to draw or who are deliberately trying to confuse you. The conjugate base of a carboxylic acid is this group called a carboxylate. It's an anion, and notice that by resonance, the negative charge can be on this oxygen and on that oxygen, shared evenly between the two. In fact, you can envision this 3-atom system having pi molecular orbitals in the very same way that we did for allyl anion. And this is an important functional group in biochemistry. Some of the protein side chains have carboxylic acid functional groups. This is another group that's important in biology and biochemistry. Some acids, as you've noticed, start out neutral and give a negatively charged conjugate base. Other acids, like hydronium, start out positively charged and give a neutral conjugate base. Both situations are okay. In this case, this functional group with the 5-membered ring containing 2 nitrogens, and both nitrogens have a proton. The formal positive charge can be on this nitrogen and on that one. That's called an imidazolium functional group. Its conjugate base is imidazole, and the positively charged imidazolium has a pKa of 6. This imidazole group is on the histidine side chain. Histidine is an amino acid that's involved in a lot of protein active sites, and it's important that its pKa is pretty close to the pH of water. That means nature can use both of these forms in chemistry. Another important functional group is the thiol. It's the sulfur equivalent of an alcohol, and its conjugate base is thiolate, and I guess you don't get to know what that pKa is. It's 8, all right? Notice that that's quite a bit more acidic than the corresponding oxygen molecule, the alcohol. And we'll talk about what that difference means and why it's that way. This is a group called phenol. It's a phenyl group plus oxygen. Sometimes people will call it phenol, but organic chemists pronounce it phenol. And I suppose if you want to annoy me, go ahead and say phenol all the time. That'd be kind of fun. I will try not to twitch too much when you say phenol. Its conjugate base is phenolate. Notice that this is quite a bit less acidic than the alcohol, even though phenol is an alcohol. And we're going to rationalize that based on the fact that through resonance we can delocalize that negative charge on the carbons that I've labeled. And we've learned that resonance is stabilizing. We'll make some more specific comparisons in a minute. I want to say a bit about the ammonium ions. These are, again, important in biology and biochemistry. The problem with ammonium ions and amines is that, like water and hydronium, they have two different acid-base reactions they can do. This is the first, positively charged nitrogen, and it can either have 1, 2, or 3 alkyl groups replacing a hydrogen. But the important point is that you've got a nitrogen with a positive formal charge and a proton. And these we call ammonium ions. They can lose a proton to become the neutral amines. And that pKa is around 11. Now, people get mixed up on this all the time. And so I'm going to try to warn you away from this mistake. The pKa of the amine going to a negatively charged conjugate base is quite a bit higher. If we scroll down here, here's a neutral amine, here's another neutral amine, both that have nitrogen-hydrogen bonds. Losing that proton to become negatively charged has a pKa of 38. And we call this negatively charged group the amide or amide anion. Either way is fine. But you can see how that can get you tripped up if you're doing a problem and you use a pKa of 11 when the situation is actually this one. You're going to get a different answer. So you got to pay attention. Am I dealing with the positively charged ammonium going to the neutral amine, or am I dealing with the neutral amine going to the negatively charged amide? All right, we've talked about water and alcohols. As we continue to rise in pKa, we're getting to things that are not very acidic at all, and yet sometimes we will use their conjugate bases as reagents in chemistry. This is an alkyne. We call it a terminal alkyne, where there's a CH group on the end on one of the sp hybridized carbons. Another word for that is acetylene, and I will use that periodically. Right? Yeah. I tell jokes periodically. Yeah. All right. It has pKa of 25, and its conjugate base is acetylide, negative charge in an sp hybridized orbital on this carbon. We'll use this quite a bit in reactions. And we'll see that this is one of the more acidic carbon-hydrogen bonds that we'll encounter. Later on, if we change the hybridization to sp2, the pKa is 40, sp3, the pKa is 50. Now you're looking at things that are not very acidic at all and can be very difficult to access as reagents. Hydrogen going to hydride has a pKa of 35, and we've already talked about these amines. Remember the trend as you go down, or as you go up, increasing numbers of pKa, you're going to weaker acids, less acidic molecules, molecules with higher energy, inaccessible LUMOs. And over on this side with the conjugate bases, as you go down, as you go up in pKa for the conjugate acid, the conjugate base is correspondingly stronger, more basic, and has the higher energy filled orbital and is therefore more reactive. Yes?
Do the asterisks you have next to different numbers indicate ones that are really important versus
Asterisks are only by -2 and 16, which are the two you should memorize. Okay. Yes, go ahead.
As far as not memorizing the rest of this goes, do you want us to just generally understand the way mechanisms work, or how would you like to?
So, yeah, how will I expect you to use pKa information? So a couple of ways. First, I will expect you to use pKa information to predict the outcome of various acid-base reactions. I will also ask you to rationalize why one acid is stronger than another. And we'll talk about the trends or the why reasons behind the pKa answers. But as an example, using pKa data to predict an acid-base equilibrium, here's one format the question could take. You're given 2 molecules on this side, 2 on this side. You don't know what the equilibrium constant is. The question asks you to predict which side dominates at equilibrium. So what you have to do is look at both sides and identify the acid and the base, or the conjugate acid / conjugate base on either side. So what do you think? Where, based on what you're seeing here, what is the acid on the left-hand side of the equation? The alcohol, right? You can tell because it loses its proton as you go from left to right. Notice that this amine could be an acid too, just not in this reaction, because you see the amine gaining a proton. So yeah, I identify the acids on both sides of the equation. Then I either remember or I go look up the pKa for those acids. So for the alcohol, I've memorized that it's 16. For the ammonium ion, I go back to my table. I am temporarily distracted by this because it looks like something I saw there, but then I realize that no, what I'm looking for is the acid form. So I bypass that 38 number, I come back here. Yes, this is what describes the going from the positively charged ammonium to the neutral amine. That pKa is 11, so we can write that down. And then the strongest acid loses its proton. I'm going to sneeze here, sorry. Nope, dang it. That was disappointing. So the strongest acid is the one with the lowest pKa. That acid wins in the sense that it loses its proton, so we would say that the left-hand side dominates at equilibrium, or that the equilibrium constant is less than 1. Okay? That's exactly the same as asking the question, can this amine deprotonate this alcohol? And the answer is no, because it's not a strong enough base to deprotonate the alcohol. The reason you know it's not a strong enough base to do this is that if you compare the pKa's on either side of the equation, you realize that equilibrium prefers starting materials. A related question we can play around with just by changing the structure of the alcohol a little bit to the carboxylic acid. There the pKa is 4, and again on this side the pKa of the ammonium is 11. So now who wins? Carboxylic acid wins in that it loses its proton, wins by losing, I guess. So equilibrium is going to favor the right side of the equation, or equilibrium constant is greater than 1. That is also the same as asking, asking the question, can this amine deprotonate this carboxylic acid? And the answer is yes, because of the pKa comparison. All right.
Can we get away with using basically just electronegativity rules for that kind of
Can
thing?
you get away with using just electronegativity rules for that kind of thing? Sort of, but you also have to know some things about resonance and also atomic size, which we'll talk about in a little bit. Okay, questions about that? I mean, another format of asking this would be, I draw some horrendous molecule that has lots of acidic groups on it, and I say, which of these can be deprotonated by this base? So if I had a base like this, and then we had some large, horrific molecule with lots of things on it, and like fangs so that you're scared. Okay, and I asked which of these acidic groups can be deprotonated by H minus. The way you do this kind of question is you first identify all the acidic groups and you find their relevant pKa's in the table. This is one area where people make mistakes. They use the table, but they misapply which pKa they need to use. This one would be 4. This is, I just happen to know because I've taught the class so many times. I didn't used to know all these numbers. I don't expect you to know them. I expect you to be able to, except for 16 and -2, expect you to be able to use the table to look up the right values. Then I'm going to write down or draw the conjugate acid of my base, and look up its pKa, which is 35. So any acids whose pKa's are lower than 35 will win by losing their proton, right? So that means this base may deprotonate any acid whose pKa is lower than 35. So let's see, that would be, and then it's just comparing numbers. Okay, and people struggle with this, and in part it's like panic by seeing the monster molecule. Yeah?
Would you give us the conjugate acid as well?
No, I would not give you the conjugate. The pKa, of the conjugate acid would be available in the table, but you'd have to draw the conjugate acid so you know what to look up. And drawing conjugate acid is as simple as saying, okay, what atom has the negative charge, and then adding a hydrogen to it. Right, H. The protons here, and I'm sorry, the electrons here end up here in the bond with the hydrogen. Okay, so we can check off this one, and that one, but not this one. This is not a strong enough acid to give up a proton to H minus. All right. The other format you'll experience this in is one that's important for biochemistry. It's one that's probably unfamiliar to you, and it's why last time we dealt with all of the horrible math, but I'm drawing a biopolymer, say a peptide or a protein, and I'm going to draw some of the side chain functional groups that are present in peptides and proteins. Not all of them, but here's some of the more important ones. Let's see, there we go. All right. And then I would tell you that we are dissolving this biopolymer in dilute buffered aqueous solution, meaning that the molecule itself will not determine the pH of the solution, but rather the solution pH is held constant, and I could choose whatever it was. In this case, we'll choose 7, but it could be 2 or whatever. And then I ask you, what should be the form of each of these side chains, its current form or a conjugate base or a conjugate acid, at pH 7. And to do this, you've got to remember what we learned last time. As I said, some of you prefer words, and others of you prefer math or equations. I'm not sure how many of the others of you there are that prefer equations. Dang it. There we go. So we've said before that for any particular acid, if the pH is greater than the pKa, then the conjugate base form dominates, whereas if pH is less than pKa, the acid form dominates. And that's the same as saying pKa minus pH equals the log of HA over A minus. So what we have to do is look at each of these groups and try to find the relevant acid-base equilibria that might apply at this pH. So I happen to know for an alcohol that there's two possible equilibria, right? There's the squiggly line here just represents, there's other stuff on the left-hand side that we don't care about right now. You've got the potential for the positively charged oxonium ion to go to the neutral alcohol, and that has a pKa of -2. But then you also have the ability of the neutral alcohol to go to the negatively charged alkoxide, pKa 16. Okay? So what I can do for each of these possibilities is to compare the pKa with the pH. At pH 7, for this top equilibrium, which side should dominate? If pH is less than pKa, then the acidic form dominates. If pH is greater than pKa, then the base form dominates. Right? So we would predict, at least at this stage, that there's none of the positively charged oxonium ion. Now, we're not done because we have to compare the pKa now of the neutral alcohol going to the alkoxide to make sure that we're not losing a proton on that alcohol. So I just compare 16 to 7. 16 is greater than 7. If pKa is greater than pH, then the acid form dominates. So that means we're also not going to have any of that. So we're going to have this as the dominant form. So that means I know this group doesn't have a positive formal charge or a negative formal charge. It's just neutral. Did you follow that reasoning? Yes?
So if the pH had been like 1, then we could have said that on this top example, it would dominate on the other side, and then it would have like a positive formal charge.
Yeah, though your pH would need to be lower than -2.
Oh,
Yeah.
Yeah.
Yep, good. Yes?
Could you explain one more time, like, I guess in the top scenario where it's OH2, like, I guess why do we consider, like, what's the situation that makes that?
Well,
Start with your OH.
right, so good. This is an important question, and it's one that people struggle with on the exam. Realize that even though I'm showing you the neutral form of this molecule, but I'm not showing you the major form of that molecule once it's dissolved in solution. When you put a molecule in solution and the solution's already buffered, and usually the buffer concentration is in the, let's say, 100 of millimolar concentration, whereas the biomolecule is in the hundreds of micromolar, and so, or less than that. And what that means is that the biomolecule is not going to determine the pH of the solution, but rather the pH of the solution is going to determine the protonation state of the biomolecule. And what that means is there's enough H3O plus and protonated buffer molecules to add protons to things if they could accept one at that pH. So maybe I'll take you through a similar example with the amine group so that you can see why this would be relevant. It just so happens here, because this pKa is so low, that no, it's not important. We can ignore it. But for amino groups, you can't. So if all you do is consider the neutral amine going to the negatively charged amide anion with a pKa of 38, you compare pH with that pKa, and you would conclude that, again, pKa greater than pH, then the acidic form dominates, so there wouldn't be any of this negatively charged one, and we would predict that that would be present. However, if you stop there, you're neglecting the fact that that amino group, depending on what the pH is, can pick up a proton from hydronium in solution or from a buffer molecule to give you the positively charged ammonium ion with the pKa of 11. So if I compare pKa 11 to pH of 7, I would also conclude that at pH 7, there's none of that there. It's actually this form that dominates. Now, where is the proton coming from? From H3O plus or from a buffer molecule. Remember that at pH 7, you've got 10 to the minus 7 molar hydronium, which doesn't sound like a lot until you realize that 1 mole is 10 to the 23rd, and so, or whatever it is. So you've still got a lot of hydronium in solution. Yeah. Sorry, Hen, go ahead.
Oh, I was just going to ask, are there any situations where when you can look at something and assume it's going to grab and
Yes, so there's situations where you need to look at something and assume it's going to grab an extra hydrogen if it can. Yes, this is it. This is that situation. The pH of the solution determines the state of the biomolecule. I realize this is a jump because you have done problems in the past where you have taken an acid and its conjugate base, say phosphoric acid and monosodium phosphate. You figured out what the pKa is. You dissolve them in solution in just such a ratio to get a target pH. That's kind of an annoying problem. It's one you can do with a calculator. It's one that only matters really if you're going to be in a lab and preparing buffers, which some of you may do, but most of you might not. But this application of the principle is important in biochemistry, because you're going to learn the structures of the amino acid side chains. Some of them are here, but you're going to need to know whether they're positively or negatively charged as a function of pH. For example, I never in a million years would draw in a pH 7 solution this neutral amine. Not going to happen because of what we've just been through. This side chain is always positively charged at pH 7. And so that becomes important to know when you're thinking about biochemical reactions. All right, any follow-up questions on that? Yes?
So is the conclusion that we came to that NH2 can exist in pH 7, just NH3?
Yes, the conclusion we came to is that by far most of the molecule will exist in this positively charged ammonium RNH3 form. Yes?
What implications does that have for cellular processes?
What implications does that have for cellular processes? Well, for protein folding, it can be very important. For example, if I conclude that this group here should actually be positively charged, then we're going to start talking about what are called non-covalent interactions between groups. Just as a preview, we'll just really quickly say the pKa of this side chain is around 4. So at pH 7, you'd expect it to exist in its conjugate base form, which would actually be negatively charged, right? And so then you can imagine in some cases this positive charge interacting with this negative charge, and that can create a driving force for the protein or peptide to bend its structure one way versus another way. All right? Maybe what we'll do at this point, well, I guess we can forge ahead. thiols have pKa's of 8. At pH 7, that proton should still be there. Alcohols we've already dealt with. How about this imidazole? The imidazole has a conjugate acid whose pKa is 6. So at pH 7, if pH is greater than pKa, the base form dominates. So that means I should be at this neutral imidazole state rather than the positively charged imidazolium. So if I'm looking at what we've summarized so far, this group should be neutral, this group should be positively charged, this group should be neutral, this group should be neutral, and that group should be negatively charged. If I were to ask this question on an exam, I would give you a molecule like this and I would say, the pH is 5. What is the formal charge on this molecule? And then you have to use the pKa information and what you know about formal charge to figure it out. And there'll be options, from is it -3? Is it -2? Is it -1? Is it 0? Is it 1? Is it 2? Is it 3? So you've got to know your stuff because you can't be off by 1. Yeah?
One more time, why the NH3, the positive form dominates?
The NH3 positive form dominates.
Technically work with the pH.
Well, actually they don't. The pKa rule only led us to conclude that there was none of this. But we have to ignore, if you just stick with this, you're ignoring this other equilibrium too.
So if it's possible to be in the other form, you can't ignore it.
That's right. If it's possible to be in another form, you can't ignore it. Fortunately, there's only 2 basically of those situations, right? You've got water and alcohols versus their oxonium ions. You've got 1 pKa here, -2. You've got another pKa here, 16. And then for the positively charged ammonium ions, 11 going to neutral amine, 38 going from neutral amine to amide. Okay? Yes?
So will those cases typically be listed right next to each other in tables?
Will those cases be, no, in general in a table they'll be listed in order of pKa. So yeah, you'll have to know what you're looking for. So this, I can guarantee you there will be a problem like this on the exam. And I guarantee you that if you do not watch yourselves, you will fall into this trap. So like Jacob, I feel like I should take off my jacket and shake it before you so that you may know that my hands are clean of your exam loss of points or something. I don't know. All right, practice that. Now, we need to, go ahead.
So just on that example, you're talking about how we need to know the formal charge of the whole thing.
Yeah,
On this one, would it just be 0?
yeah, and this one would be 0 because the pluses cancel out the minuses. Yep.
Gotcha.
All right. Well, we need now to figure out how to rationalize differences in acidity because you're not always going to have a pKa table. But even without pKa, I mean, you'll always have one on the exam, but in your life, I suppose, you won't always have a pKa table. So we want to know some of the whys behind the pKa trends. And it basically comes down to 2 things, potential energy and kinetic energy. So we are going to rationalize the strength of acids by looking at how stable the conjugate base is. That is, how much that conjugate base can tolerate a negative charge. But we already know 2 things that make electrons move lower in energy, right? Electrons can have lower potential energy, and by potential energy we mean closeness or proximity to the nucleus. And this is going to reveal itself in the principle of electronegativity. I totally did not understand this, and maybe still don't, but I was taught that electronegativity is how much an atom wants electrons, which is a reasonable summary, but of course atoms don't want anything that we know of. And so why would one atom attract electrons more than another? And as you go across a row of the periodic table, we'll start with carbon, nitrogen, oxygen, and fluorine. With each as you go from carbon to nitrogen to oxygen to fluorine, you're adding a proton to the nucleus, right? The nucleus is getting increasingly positively charged. And you can look at the number there, 6, 7, 8, 9. And what's interesting is that electrons within the same shell, the same principal quantum number energy level, don't really shield each other from the nucleus. So you can think of each electron in these atoms as experiencing the full charge of the nucleus. Now, supposedly once a shell is completed, the next principal quantum number moves the electrons out even further from the nucleus, and so then there's this thing called nuclear shielding, where the outer electrons don't feel as much of the nucleus because the inner electrons shield them. But within a valence shell, there's not as much shielding. So you would predict that, what I've written here is nuclear charge. The nuclear charge felt by the valence shell electrons increases as we go across the periodic table. Stronger nucleus ought to pull the electrons closer, right? And closer to the nucleus is lower in energy. So, and this follows a couple of different trends. So you've got atomic size across a row of the periodic table, and it's decreasing. And then you also have electronegativity, which is increasing. All of these are manifestations of the same basic phenomenon, that on fluorine, the nucleus is more positively charged, electrons are held closer to the nucleus, so they should be lower in energy. If we think about, if we were to write here lone pair energy on each of these atoms, it would be higher here, going to lower there. All right? Now let's compare pKa's with this same trend in mind. So, and we'll write the acid and its conjugate base. We'll do the same for the amine going to the negatively charged amide, for the alcohol going to the negatively charged alkoxide, and for HF going to negatively charged fluoride anion. And we'll write the pKa's of those processes: 50, 38, 16, and 4. See what a big difference that makes across the row of a periodic table? And this is a potential energy argument. The electrons on fluorine are held closer to the nucleus and therefore are lower in energy. All right? And the reason we're going to use this potential energy argument is because though size is changing as we go across a row of the periodic table, it's not changing a lot. The major thing that's changing is the charge of the nucleus. So we're not worrying about, remember, size, well, we'll talk about kinetic energy in a minute. But do you get that rationale that the HF is stronger acid than, say, water or alcohol because of the increased electronegativity of fluoride versus oxygen? Yeah.
So basically, to summarize, everything else being equal, as we move to the right across a row of the periodic table, pKa decreases.
That's right. All other things being equal in a row of the periodic table, as you move to the right, pKa should decrease. Do I see another hand back here? No? Okay. Yes?
So, and that's just because as you get as the electrons get pulled closer to the nucleus, they're more stable, so there's more added they can add it. They can handle it better, right?
Right. As electrons are closer to the nucleus. That's right. When we go to the conjugate base and we have an extra negative charge, those electrons are going to be lower, closer to the nucleus. Yeah. Another manifestation of this principle is a difference that you may have noted before when we were dealing with carbon-based acids, the acetylide, the sp2 hybridized alkene, and then say the sp3 hybridized CH bond. If you look at the pKa's of those protons, they are 25, 40, and like 50. And the reason, presumably, if you look at the conjugate base, is that in the acetylide, the negative charge is held in an sp atomic orbital. In the alkene, negatively charged alkene, it's in an sp2 orbital, and in the negatively charged alkane, it's in an sp3 orbital. Now, how does this follow the electronegativity argument? What did you learn about S? Go ahead.
It's about S characteristics and P characteristics, because S orbitals keep electrons closer towards the nucleus.
Great, yes, that's exactly right. It's about S character versus P character in these hybrid orbitals. S is closer to the nucleus, P is further from the nucleus. Therefore, the more S an orbital has, the closer it holds electrons to the nucleus. So by the same principle as electronegativity, the negatively charged acetylide is more stable than the negatively charged alkane, right? And so you can think of sp orbitals or sp hybridized carbons as actually being more electronegative than hydrogen, or more electronegative than, whoops, that wasn't what we wanted to do. sp hybridized carbons is more electronegative than sp2 and sp3. Now, I can't think of many more situations other than this one where that principle applies, but it's another manifestation of the same idea that electronegativity is related to proximity to the nucleus. The closer you are to the nucleus, the more stable. All other things being equal. Right, so now we need to deal with the second principle. And to illustrate this, we want to consider the acids of the halogen acids, HF, HCl, HBr, and HI, whose pKa's go in a direction that you may not think. I always forget what these are, and it doesn't totally matter. The important principle is here, iodide, HI is most acidic, and HF is least acidic. However, F minus is most electronegative, and I minus is least electronegative. What's going on here? And the idea here is the size of the atom that bears the negative charge is changing dramatically. So iodide is quite a bit bigger than fluoride. And it's not the same as the difference between carbon, nitrogen, and oxygen. If you've looked at space filling models before of atoms, carbon, nitrogen, and oxygen are all about similar size, a little bit smaller. Fluorine's a little bit smaller. Size does decrease as you go across the table, but not a huge amount. In contrast, size increases a lot as you go down a column. Because, again, as you fill a valence shell, the inner electrons shield the outer electrons from the nucleus, and the outer electrons don't experience as much of the nucleus. So the outer electrons are more spread out and occupy more space. So what we might say here, I need to decrease the size a little bit. Oops, that's probably too much. Is that because of the difference in size, the negative charge is more spread out, whereas on fluoride it is localized. And now, what happens when electron density gets spread out? We call that electron delocalization. So why is electron delocalization stabilizing?
Because the electrons are further apart, so they're not repelling each other.
Okay, that's an interesting idea I actually hadn't considered. Yeah, as electrons are further apart, occupy more space, They maybe don't repel each other as much. That sounds like a good argument. That's also a potential energy argument. Another thing to consider is the kinetic energy. Do you remember we talked about how wave functions that don't change shape as often, change shape more slowly, have lower kinetic energy? And so if you're iodide, your wave functions are spread out quite a bit, whereas if you're fluoride, they're quite narrow. And so we'll see that electrons on iodide have lower kinetic energy than electrons on fluoride because they're more spread out. So this is why we talked about kinetic energy in that pesky second derivative in the first class, because I wanted you to know why having spread out electron density is a good thing, or a favorable stabilizing thing. Another example of this principle that spreading out electron density is favorable is the comparison between the acid alcohol, which has a pKa of 16, versus the acid phenol, which has a pKa. Oh, let's see. No, totally want to do that yet. Do that in a minute. Versus the carboxylic acid, which has a pKa of 4. Okay, why should the pKa of this be greater than this? In the conjugate base, the negative charge is held on the same kind of atom. Yeah.
Because it's resonance.
Resonance delocalization, which should be stabilizing because more spread out wave functions have lower kinetic energy. All right? Now, maybe let's add phenol to the comparison. This is an interesting interplay between both concepts that we've talked about, potential and kinetic energy, electronegativity versus delocalization. Why do you suppose that the pKa of phenol is so much higher than that of the carboxylic acid when in the phenol you can delocalize these electrons in more places? Yeah?
Because we have to change the sp characteristics of the molecules.
Okay, change the S, I'm sorry, can you explain that?
So you have to move atoms around.
Okay, you can actually push electrons from one place to another in phenol, keeping everything the same except for where the electrons are. So by resonance, and this is something to practice as well, especially if you're having difficulty seeing why I highlighted those carbons, that would be worth some practice. I can share the electron on the oxygen, the negative charge on the oxygen with this carbon, and then with this one and with this one through steps like this. So why more places to delocalize, but still not, yeah, go ahead. Bingo, carbon's much less electronegative than oxygen. So resonance stabilization is good, but compared to, if you have to choose between resonance stabilization on oxygens versus resonance stabilization on oxygen versus carbons, it's more stabilizing on the more electronegative atoms. All right. One sort of last manifestation of spreading out electron density, we can compare carboxylic acids like acetic acid, which has a pKa of 4, and then I should have looked up this number, but the number doesn't really matter. Oh, no, don't have it. If we put electronegative groups on the adjacent carbon, compare these two acids, and I'll just say the pKa of this one is, I don't know, I'm going to guess 2. I know it's more acidic. Compare these two molecules. They're both, the conjugate bases are both resonance stabilized. They're on the same kind of atom. The only difference is you've got fluorines on the adjacent carbon versus hydrogens. What's happening here is that in each of these carbon-fluorine bonds, we're pulling electrons away from the carbon towards fluorine because fluorine's more electronegative. That makes this carbon electron poor, and it begins to pull electron density from the adjacent carbon. and that tends to stabilize this negative charge by allowing some of that charge to sort of lean towards the fluorines. That's also electron delocalization, but it's not resonance. It's called an inductive effect. All right, that basically does it for chapter 2. We'll start chapter 3 next time.